Hello everyone, Kodongwane, the Native God here. Trust everyone is doing okay and that you are finding the content of this YouTube channel helpful, right? Of which, if you do find it helpful, please like and subscribe to the channel, right? Also, if you do find it helpful, I'm sure your fellow students are going to find it helpful as well. So in liking and subscribing to the channel, please share to your fellow students as well, right? Now today we are looking at, or we'll be looking at, a topic based on Mechanotechnics N4 called hydraulic systems, right? Now under hydraulic systems, we basically look at the application of Bolis Theorem for pipes, for horizontal tapered pipes, and vertical tapered pipes, as well as tapered pipes that are at an incline or that are at an angle with the horizontal, right? Where we don't consider losses or where we ignore losses. And then we also look at the application of Bernoulli's, right, where we consider losses and look at problems from the perspective of Darcy and Chassis formula, right? So Darcy and Chassis formula we use when we are considering losses for horizontal pipes, as well as if you're looking at a problem based on maybe the flow of water through two reservoirs, right? And then we also look at the application of Bernoulli's in measurement of flow, right, where we look at flow through an orifice as well as flow through a venturimeter, right? So first we're going to look at applying Bernoulli's theorem, right, for horizontal tapered pipes, right? And then in the playlist, or in the playlist for hydraulic systems, right, we are going to tap into the other units as well, right, the ones I've just mentioned. Now let's consider the problem right in front of us, right, where we have a horizontal tapered pipe, right, and the problem reads as follows: a pipe of diameter 100 millimeters tapers to 200 millimeters diameter in the direction of the water flow, right? Now that means that the water is flowing in this direction, right? Which is flowing in this direction. Right, because they said basically the direction of flow follows the taper of the pipe. So as the pipe tapers from a smaller diameter to a bigger diameter, right, the water flow follows that direction, right? Now the quantity of water flowing through the pipe is 10 liters per second. A pressure gauge at the 100 millimeter diameter end of the pipe shows a reading of 20 kilopascals. See the figure below. Calculate the pressure at the 200 millimeter diameter pipe section, right? Now it is important to note that for horizontal pipes, or for horizontal tapered pipes, right, in fact, for when applying Bernoulli's in a problem where you're looking at flow through a pipe, right, whether the pipe is horizontal or it is at an incline or it is a vertical pipe, right, where the water is entering, you take that section as 1, and where the water is exiting, you take that section as 2, right? So since we've already established the direction of the water, it means that, right, it means that this side of the pipe is where the water enters, right? Hence this side will be 0.1, right? The water goes in this direction, right? The water goes in this direction, hence this side of the pipe is called 0.2, right? So the entry side of the pipe is named 0.1 and the exit side of the pipe is named 0.2, right? So always remember to get that right, because you don't want to mix the two up because it's going to mess up our calculations, right? So the entry side of the pipe is 1 and the exit side of the pipe is 2, right? Now let's see what we've been given here, right? Before we look at what we've been given, right? When looking at problems based on hydraulic systems, right? If you're looking at the unit we're looking at right now, where we're looking at the application of Bernoulli's through flow in a pipe, right? Whether the pipe is vertical, at an incline, or horizontal, right? We look at whether or not the fluid is accelerating or decelerating, right? That will help us in determining where the pressure, right, will be greater and where the pressure will be lower between section 1 and section 2, right? That is important to determine so that when you go through the solution, right, by the time you get to whatever it is you're looking for, you already know, right, before you even do the solution, you know what to expect already, right? This is what I mean by that, right? So you have point 1, right? If you look at the section 1 of the pipe, it is smaller than section 2 of the pipe, right? Section 1 is 100 millimeters in diameter and section 2 is 200 millimeters in diameter, right? Meaning what as far as velocity, right? Now, is the velocity greater at 1 or is it greater at 2, right? The velocity through flow in a pipe, right, is always greater in the smaller section of the pipe, right? A typical example of that is if you watering your garden, maybe at home, right? Just using a hose without any nozzle that can manipulate the velocity of the water, right? When you're watering your garden, think about what happens as soon as you constrict the diameter of the pipe, right, where the water is exiting, right? If you think about it, what happens to the velocity of the water, right? The velocity of the water goes faster. As soon as you constrict or as soon as you make the area or the diameter of the pipe smaller, right, the velocity of the water goes faster, right? Meaning what? Meaning that when the pipe diameter is smaller, right, the velocity of the water goes faster, and if the diameter of the water is bigger, right, the velocity of the water goes slower, right? So we expect for the velocity of water to go faster at the smaller section of the pipe than it would on the bigger section of the pipe. Meaning what? Meaning that we expect V1, since it's the smaller section, to be greater than V2, right? So whatever V1 and V2 is, V1 has to be greater than V2, right? So we can use that, right? We can use that to check our answers. So if your answer for V1 is greater than V2, then there's a good chance that you will be right, right? Now, we can do the same thing with pressure, right? Remember what Bernoulli's theorem stands for, right? Bernoulli's theorem essentially states that in the increase, right, it states that when the velocity of the water increases, right, or when the velocity of a fluid increases, whether the fluid is a liquid or a gas, right, when the velocity of a fluid increases, right, the pressure within the fluid decreases, right? That is for horizontal pipes, right? So Bernoulli's theorem states that for horizontal pipes, right, or for a medium that is horizontal, because this doesn't just apply to pipes only, right? So if the medium we are looking at is horizontal, right, if the velocity of the fluid increases, or as the velocity of the fluid increases, right, the pressure within the fluid, right, decreases. Now mathematically we can explain that using dynamics, right, by looking at if the water is accelerating or decelerating, right? So as we've established that V1 is greater than V2, it means that the water, right, within the horizontal tapered pipe is what is decelerating. Now, as we know, deceleration, as far as the direction of acceleration, will be in the negative direction, right? Acceleration is in that direction, right, the positive direction, and deceleration, since it's negative, right, is going to go in this direction, right? Now, since we've established that the water is decelerating, it means that acceleration is in that direction. Now we have F2 this side going in this direction, and we have F1 going in that direction, right? Now, as far as dynamics, we say that the forces going in the same direction as acceleration, right, we take them as positive, or we say are greater than the forces going against acceleration. So in this case, the force going in the same direction as acceleration is F2. So F2 is greater than any and all forces going against acceleration. Forces going against acceleration is F1. So F2 is greater than F1, meaning that even P2 will be greater than P1, right? So we can use this as reference when having to calculate any of the pressures between P2 and P1, depending on what you've been given and what you're looking for, right? But by doing this gives you an idea of what to expect, right? We expect P2 to be greater than P1, and we expect V1 to be greater than V2, right? Now let's look at what you've been given, right? Now, as far as what you've been given, we have D1 is 0.1 meters, right? D2 is 0.2 meters, right? We also are given P1, right? So P1 is equal to, P1 is equal to 20 kilopascals, right? We are also given Q. They say the quantity of water flowing through the pipe is 10 liters per second, right? So we also have Q. The flow of water within the pipe is 10 liters per second, right? Now 10 liters per second, remember, as far as the flow rate of the water, it has to be in meter cubed, right, or in cubic meters per second, right? So we convert the liters to cubic meters, right? In doing that, you divide the 10 by 1,000, right? Now in dividing the 10 by 1,000, Q will end up being 0.01. So this will be 0.01 cubic meters per second, right? So that's the value of Q, right? Now we do not have V1, we also do not have V2, we also do not have P2, right? Right, now let's look at the question. Calculate the pressure at the 200 millimeter diameter pipe section. Right, now the 200 millimeter diameter pipe section is the two section or the exit section of the pipe. So essentially we know they are looking for P2, right? Now in determining the P2, we need to apply Bernoulli's principle, right? Now in applying Bernoulli's principle, it means you have to use Bernoulli's equation, right, in determining P2. Now Bernoulli's equation, right? Bernoulli's equation, we have three variations of Bernoulli's equation, right? We have one that is energy per unit volume, we have one that is energy per unit mass, and we have one which is energy per unit weight, right? Now you can use any of the three variations of Bernoulli, right, depending on which one is convenient to use, right? Now, meaning, for instance, if you look at energy per unit volume, right, if you look at energy per unit volume, each of the terms in the equation is in terms of pressure, right? So each of the terms is in terms of Pascal, right? When you look at energy per unit mass, each of the terms is in terms of velocity, meaning that each of the terms is in terms of meters per second, right? So if you have, or if you're looking for velocity, right, it's much easier to just use the variation of Bernoulli's that is in terms of meters per second, which is the energy per unit mass. Now, if you're looking for height, right, whether it's H1 or H2, it's better to use, or it is convenient to use, the variation of Bernoulli, which is in terms of height, which would be the energy per unit mass, per unit weight, sorry, right? If you look at each of the terms in this variation of Bernoulli, right, each of the terms is in terms of meters, meaning that each of the terms is in terms of height, right? Now, aside from that, right, you don't really need to memorize all of these variations of Bernoulli. You can just stick to one and then manipulate the one as and when you need to, right? So we are going to, or I am going to be using this variation of Bernoulli, right, because this one is in terms of pressure and I'm looking for P2, right? So it's convenient to use this variation of Bernoulli, which is energy per unit volume, right? Right, now I forgot to mention something here, right? Now, if you look at the variations of Bernoulli, right, each term represents some kind of energy, right? This term, right, represents pressure energy, right? The term with the velocity represents kinetic energy, right? And the term with the h or height represents potential energy, right? Now, it means that in applying Bernoulli's, right, you have to have pressure, you have to have velocity, and you have to have height, right? Now, as we've established that we don't have the velocities for either of the sections, right, in the horizontal tapered pipe, right? As far as height, right, for a horizontal pipe, the height, so H1, right, H1 will be equal to H2, right? If the pipe is horizontal, whether it's tapered or not, if the pipe is horizontal, then the H, right, the height in section 1 and section 2 will be equal, right? So when applying Bernoulli's, right, whether you've been given the height or not, doesn't really matter because it's going to cancel anyway, right? Right, so in applying Bernoulli's, we're going to need V1 as well as V2. So first we calculate V1 and V2, and then we apply Bernoulli's to calculate P2, right? Now, as far as calculating V, depending on what you've been given, right, you can always use the formula for Q if you've been given Q. If you haven't been given Q and you've been given maybe one of the velocities, right, and the diameters of each of the sections, then you can just use the continuity equation, right? But we'll look at a problem where we have to use the continuity equation, right, later, right? Right now, the problem we're looking at, we've been given Q, and Q is equal throughout the fluid's motion, right? Meaning that the Q at 1 is equal to the Q at 2, right? So the Q is constant, meaning that we can use the same Q to calculate the V at section 1 and the V at section 2, right? So we know Q is equal to A times V, so the area of the pipe times the velocity of the pipe. So looking at section 1, A1 times V1 is equal to Q, right? So in calculating V, it means you have to divide both sides by the area, right? And then this cancels, therefore V1 will be equal to Q over the area 1. Now we know the area is pi over 4 times d squared, right, which will work out as Q times 4 over pi times d1 squared, right? And then of course we substitute, so V1 will be equal to, now in substituting right? Q we know is equal to the 0,01 times the 4 over pi times d1 is 0,1, so 0,1 squared, right? Now in calculating this, right, we will get 1,273 meters per second, right? So v1 is equal to 1,273 meters per second, right? Right, now in calculating v2, right, we're going to use the very same formula, because as we've established, the flow rate is the same throughout the fluid's motion, right? So essentially for v2 we are going to do the same. So v2 will be equal to q times 4 over pi times d2 now, so d2 squared, right? So q is 0,01 times the 4 over pi times d2 squared. d2 is 200 millimeters, so that's 0,2 squared. Now if you punch that in your calculators, you're going to get 0,318 meters per second, right? Now as we established earlier that v1 is going to be greater than v2, right, our calculations just confirm that v1 really is greater than v2, right? Meaning it's likely that we are on the right path, right? So since we have v1 and v2, we'll now be able to apply Bernoulli's theorem, right, in the motion of the fluid for this problem, right? And applying Bernoulli's, we're going to use the variation which is convenient for calculating pressure. That's energy per unit volume. So P1 plus half rho V1 squared plus rho GH1 is equal to P2 plus half rho V2 squared plus the rho GH2, right? Now for horizontal pipe, as we established that the H is equal, meaning that since the H is equal, right, the rho GH is going to cancel each other out, right? Meaning manipulating the formula for P2 will be equal to P1 plus half rho V1 squared, right, minus half rho V2 squared, right? And then we simply just substitute, right? P1 is equal to 20 kilopascals. Now in substituting, we have to make sure that the pressure is in terms of pascals. The 20 kilopascals is the same as 20 times 1000, so times 10 to the 3. Now this is in terms of pascals, plus half rho is the density of water, right? The density of water we take as 1000, right, unless it's been stipulated otherwise, right? So since it hasn't been stipulated otherwise, we are going to use 1000 as the density of water times V1. V1 is 1,273 squared minus half rho of water is 1000 times V2. V2 is 0,318 squared, right? Now if you punch this in your calculators, you are going to get 20,76 kilopascals, right? Now earlier when we were doing our free body diagram, right, we determined that P2 will be greater than P1. Now if you look at P2, right, P1 is 20 kilopascals, P2 is 20,76 kilopascals, right? Meaning what? Meaning that it is likely that we are correct, since P2 really is greater than P1, right? Right, so for problems based on horizontal tapered pipes, this is the approach you would take, right? Right, hope you find this helpful. If you did, please like and subscribe. Also share the content with your fellow students. See you in the next video.